Today we're going to talk about Hess's law. So Hess's law states that in going from a particular set of reactants to a particular set of products, the change in enthalpy is going to be the same, whether the reaction takes place in one step or in a series of steps. And just as a reminder, enthalpy is the total heat content of a system, including the external pressure done upon it. So how does this law work? Why does it work? Well, it works because enthalpy is a state function, which means that it doesn't matter how many steps you get to the final enthalpy, the enthalpy is still going to remain the same. So, when you're working with Hess's law problems, you're usually going to get more than two equations, and in this case, I'm just going to write one down for the sake of explaining. So, it's just going to be a standard equation, like this. Sorry. And then it's also going to give you its enthalpy, which in this case it's 251 kilojoules. So what can you do with this equation? Well, Hess's law states, well, not necessarily states, but it allows you to be able to multiply this entire equation by a constant, because if you multiply a constant, the ratio of the products to reactants are still going to remain the same. So for example, I can multiply this whole equation by 2 and it would look like this. And in doing so, even though the size of my products to reactants changed, but the ratio still remains the same, and that's the important part. And when you multiply your entire equation by 2, you also have to multiply your heat of formation by 2, which in this case, let me pull out a calculator. Oh, sorry about that. Okay, 251 multiplied by 2. So 502. So now it's going to be negative 502 kilojoules. Okay, you can do that, or if the situation required you to do it, you can make this reaction from an endothermic to an exothermic. So in this case, this reaction is an endothermic, and sometimes you need to make the equation into exothermic. So how would that look like? So you would just flip the products with the reactants, right? Okay, so it will be like this. Sorry about my bad handwriting. Anyway, so in doing so, you're changing it from an endothermic to an exothermic. So that means you have to switch the signs of your enthalpy, because now it's the opposite. So now the enthalpy is going to be positive 251 kilojoules. So why would you need to do this? Well, here's an example problem. It might be clear as we go along. So, in a problem, they give us this equation. Well, these two equations actually. And your goal is to try to manipulate these two equations to look like the original equation, which is nitrogen plus oxygen equals nitrogen dioxide. So how are you going to do that? Well, first of all, you're going to check what are the reactants and what are the products, and are they on the right side of the equations. So first we look at the reactants. Our reactants are nitrogen and oxygen. Do we have nitrogen and oxygen on the right side? I see we have a nitrogen here, and we have actually two oxygens right here, so we're good to go on the reaction side. So we have nitrogen dioxide as our products, right? Oh, sorry about that. I forgot an 2 over here. Okay, I swear that was what was given to me, so sorry about that. Yeah. So we're also good on the product side, because our products in our original equation is 2NO2, and we have a 2NO2 here. Alright, so how are you going to manipulate this to look like the final equation? Well, it doesn't look like you need too much manipulating because everything seems to be there. Because in your product side you need 2 oxygens, and you got 2 oxygens, and you also only need 1 nitrogen, so you've got 1 nitrogen there. And you've got your 2 nitrogen dioxide on the product side. So the only thing that seems to be like additional to these 2 equations would be the 2 NO. So fortunately they're on opposite sides, so you can just cancel these 2 out. Sorry about the redundancy with the red. And then after all of that, you can just add your 2 equations. So that will look like that. Oh, and just a reminder, even though you cross out your 2NO, it doesn't change your heat enthalpy, because you're adding them and they kind of just cross out. Anyway, so when you do that, you also have to add your enthalpy right here. So let's take a calculator out and take a look at that. Okay, so we have 108 minus 102, 12. Okay, which gives you a heat enthalpy of 68. Alright, so does this equation look familiar? It should, because when you look at it, it's the exact same one as we started out with. And just to double check, our heat of formations are the same. And that's a simple example of Hess's law problem, and we'll get more complicated as we go along.
Next example we're going to do is one with 3 equations given, and we're going to find the change in enthalpy for NO plus O to NO2. So first we're going to make sure we know which ones are the reactants and which ones are the products. So NO and O are both reactants, so we find those in the original equations. O is a product in the second blue equation, and NO is a reactant in the third purple equation. And the reactant of the original equation is NO2, which is on the right side for the purple equation, so we're all set there. So what we're going to do first is that we're going to have to reverse the blue equation because O has to be a reactant and on the left side. So I will rewrite it reversed. And so the change in enthalpy, it's going to have to be negative instead of positive because it becomes an exothermic reaction. Okay, so I'm also going to copy down the purple equation from above because it's already in the correct orientation. And so the change in enthalpy is going to be untouched. Now, the red equation, we see that O2 is a product over here in the blue equation. So we need to reverse the red equation so that it becomes a reactant so that it can cancel out with the right side. So I'll also reverse the red equation. And so this is also going to change sign because it becomes an endothermic reaction. And so now we see that the O3 right here on the red equation needs to be cancelled out with the O3 in the purple equation, but the red equation, it's a coefficient 2, so we're going to have to multiply through the purple equation by 2 all the way through. And so the enthalpy change of that equation is no longer 199, but negative 398 kilojoules because you're going to have to multiply that number by 2. So now that I have those three equations in the correct orientations, I can cancel out what I have. So the 203 and the 203 will cancel. The 302 and the 202 and the 102 will also cancel. And so you will end up getting 2O plus 2NO goes to 2NO2. And adding these three enthalpy changes up, you get negative 466 kilojoules. But we have to notice that in the original equation above, right here, that all the coefficients are 1. So you're going to have to divide this equation by 2. So your final answer for the equation that they want you to get is going to be negative 466 divided by 2, which is negative 233.